Hi, my name is Adina. I'm from the Institute of Neuroscience and Medicine at the Research Center in Jülich, and I'm going to introduce you to the software tool DataLad today. Here is what you will have learned at the end of the session. You will know why it is useful to use version control not only for your code and manuscripts, but also for all other aspects of your research, for example, data. You will get to know the Yoda principles for reproducible and intuitively structured data analysis, and you will learn about DataLad, in particular the relevant commands to consume and create so-called DataLad datasets, to version control files regardless of their file size inside of them, link the various components of a data analysis together, and run and rerun computationally reproducible data analysis. This session will contain references to tools that you've already learned about, in particular the version control tool Git and the concept of software containers. At the same time, this session today will lay the foundations for next week's session on the execution and environment manager ReproNim. Now, what is DataLad? DataLad is a command line tool that assists with data management and data publication. It builds on two version control tools, Git, which you already know about, and Git Annex. Among its main features are version control for arbitrarily large content, transport mechanisms for sharing and obtaining data, and commands and concepts for computationally reproducible data analysis. You can see that my recording contains the slides on the right-hand side and my computer's terminal on the left. If you want to, you can not only listen to my talk, but also follow along to the coding examples that I will be demonstrating in my terminal. If you follow the link on the slide, right here, you can find the code that I'm executing to copy and paste into your own terminal, and you will also find additional explanations and references. You can see in my terminal that I'm running datalad --version to print my software version of DataLad. You should make sure to have version 0.13.6 or higher installed if you're coding along, and you should also make sure to have a configured Git identity so that Git knows your name and email address. If you have used Git before, then you will likely have done this already. Just for completeness, I've included it here in my codecasts. Okay. In order to install DataLad, if you haven't done so yet, please go to handbook.datalad.org and find installation and configuration instructions for your operating system. Should you have questions or run into problems, you can get help by opening an issue on the GitHub repositories of the handbook or of DataLad itself. Alright, whenever you use DataLad, then you will do this in what is called a dataset. A dataset is simply a directory on your computer that is managed by DataLad, and on first sight, a DataLad dataset really looks just like any other directory on your computer. Here, for example, you can see two screenshots of the same dataset, one in a file manager, one in a terminal. And this may sound super familiar because you experienced something similar already with Git repositories. It's just a directory where you point a software to in order to have it managed. And this isn't far off at all, actually, because the DataLad dataset is a Git repository. It just has more features, and those features can improve your science and data analysis further than Git alone can. Now, in order to get a dataset, you can either create a new dataset from scratch or transform an existing directory or Git repository into a dataset, or you can install a dataset from somewhere else. You will see both options in this session, but in order to demonstrate the first set of features of datasets, I'm starting with creating a dataset from scratch. So let's take a look at the basics. First, I'm creating a new dataset from scratch, and I will use that to demonstrate some basic functionality in the narrative of a small toy data analysis. I'm doing the creation with the datalad create command. This command takes a name, in this case my analysis, and it will create a new directory under this name and instruct DataLad to manage it. Here the command also has an additional option, the -c option, which is used to configure datasets in a certain way at the time of creation. This configuration, or procedure as it is called, has the name Yoda, and this configuration prepares a dataset for data analysis with a bit of useful structuring and settings. Now, if I list the directory structure inside of this newly created dataset with the Unix tree command, you can see some of the things that this procedure has done, because the dataset isn't empty, but it has a code directory in which you can place your scripts, and it has plenty of documentation files that you can use to document your analysis for others and your future self. Okay, so one feature of DataLad is version control, and the first hint towards this is if you take a look into the dataset and also list all of the hidden files, you can see these hidden dot files or dot directories. And these belong to the version control tools that work in the background. Now, I will use a very simplistic example to demonstrate how easy version control is. For this, I will just start by removing placeholders in the README files that are included in this dataset. And I'm doing this in my remote control terminal by just echoing an empty space inside of them. That's easier for me, but you can also just use an editor of your choice if you want to. Now, these two files were already managed by DataLad. There is a command called DataLad status that reports on the state of the dataset. With the change that I have just done, I have modified files that were already under version control, and therefore in the DataLad status query, these two files show up as being modified. I can also use Git tools, for example Git diff, to find out more about the changes between the current state and the last saved version of this file. And you can see everything that has been removed highlighted in red and everything that has been added highlighted in green. If I decide now that this is a worthwhile addition to the dataset, I can record the current dataset state using the DataLad save command. This command will save all of the modifications in the dataset. In order to build a human readable history, I'm also attaching a concise commit message that summarizes my changes with the -m, which is short for -- message option. And that was it. Saved. This is different than how you would use Git. And you should note that DataLad save saves all of the dataset modifications, so all untracked or modified files. This saving of everything is not always desirable. So now I'm going to show you how to save specific modifications only. And for this, I'm downloading a file into the dataset. In this case, it's an XKCD comic that I'm retrieving with the Unix command wget. But I'm also modifying one of the readmes by giving my project a description. So now I have two modifications in my dataset. Here you can see them reported from DataLad status, and they are unrelated. It is not good practice to save unrelated changes together, so you should separate them. You should always work under the assumption that you may want to revert a change that you have done, and thus an individual change should be quite self-contained and not include additional work that doesn't have anything to do with what you may want to revert. So to separate those two changes, I'm saving them individually. And with DataLad, I can do this by adding a path to DataLad save. So first, I'm saving the README, and I'm again attaching a nice commit message. And then after this is saved, I can do another save to save the remainder of changes and thus save the comic that I have added to my dataset. Cool. And after these few changes, I have already built a small version history of my dataset, and I can then use tools like git log, because this version history is nothing but the Git history, to take a look at it or interact with it. And I can even, for example, query individual files on how they evolved by, for example, just running git log on a particular file. And what I'm seeing here is this file's Git history. Cool. So procedurally, version control is super easy with DataLad. You can modify the dataset and then you can save the changes with a single command. And if you only save meaningful units of change and attach helpful commit messages, then you can also grow a nice version history of everything that has been done. And this version history is super useful because it can become a complete research log for you and others to find out what was done, when, by whom, and how. Importantly, you can use DataLad to version control data of any size. So not only README files, but also neuroimaging data, movies, your music collection, anything. And it is quite important to do this, because data changes, just like code does. It changes because errors are fixed, data is extended, file naming standards change, you might be using a different subset of data for a second rerun of your data analysis. There are many, many reasons. But it is very important to capture what happens to data and also which versions of data are used for a data analysis, because the underlying data is fundamental to the results that you obtain. And without knowing precisely which data an analysis was run on, it is very difficult to reproduce a scientific finding. But by version controlling also data, you have a history of what happened, and you can identify each version of this history uniquely. But before I show you how to use DataLad for analysis and linking data and precise versions to code and results, there are a few more features that I want to demonstrate. The first is a sneak peek into provenance capture. Dr. Matone has already talked about digital provenance in week 5. It's an important part of fair data management, and it makes your life and others' lives a lot easier. Now, in a dataset, you're already capturing some provenance. For example, who did it change and when. But there's a command that captures some more provenance, namely the origin of a file. And this command is called DataLad download URL. I'm going to show you how I use this command right now. What I'm giving to this command is a URL, in this case to another webcomic, a commit message, and a file name. I'm hiding this little file here by giving it a file name that starts with a dot, because on Unix-like systems, dot files are hidden, so I've placed a little Easter egg inside of my dataset so that people that can look at my data analysis will find something funny. If I execute this command, then DataLad will download the file from the URL. It will save it under the file name and with the provided commit message, and importantly, register the origin of this file in the background. And this is helpful in many ways. At the moment, it is convenient because it spares me a DataLad save. But later, I will use the provenance that has been registered in the background to demonstrate a very important principle of DataLad. Okay, but first, let me quickly summarize what has happened so far. You can create a DataLad dataset with DataLad create. There are procedures such as Yoda that are useful, and I will give you some details on this soon. A dataset builds up a Git history, and tools that can visualize this history, like Tick or GitLog, can be used to explore this history and interact with it. DataLad save records the dataset or file state into history. This does version control with fewer commands than Git, and you may find it easier, but you could also use Git commands in DataLad datasets. In any case, make sure to attach commit messages that summarize the change for future you and others to have a nice human-readable dataset history. DataLad download URLs obtains web content and saves it together with its origin. And finally, DataLad status reports the current state of the dataset. It is good practice to have what is called a clean dataset state with no modifications or untracked files. Okay, next, I want to show you how you can consume datasets. A dataset can be created from scratch, but it can also be installed from a URL or path. For example, someone could publish a dataset to a public place like GitHub, and you can clone it from there. And consuming datasets like this is a widely popular use case for DataLad because it provides you with streamlined procedures for data access, retrieval, and updating. For example, let me go out of this dataset that I've created and install some neuroimaging data. It's the same that you can see in the slides in this GIF. What I'm installing here is the Study Forest dataset, and I'm installing it from a public GitHub URL. For this, I'm using the DataLad clone command, which only takes this URL at the moment. Something that is really peculiar here is how fast this installation is, because this dataset is a neuroimaging dataset that tracks many gigabytes of files, but the installation took only a few seconds. And if I then take a look inside of this dataset and list the file contents, then I can browse through all of these files. The reason why it was so fast, even though there are so many files inside of them, is that most of the files in this dataset don't contain any content yet. And this leads to a really small size. So if I run the du disk usage command, then it reports that the overall size of the dataset is just a few megabytes. But with this dataset, I now have access to all file contents that are inside of this on demand, and I can retrieve file contents using another command that is called DataLad get. Here's how that looks like. What I'm doing here is that I am specifying a path to the nifty files across all runs of a localizer task for one subject in this dataset. And when I execute this command, then DataLad get will retrieve the file contents of all of these files. Now, with these concepts, we don't only have streamlined data download and access, but what this allows me is to have access to more data than my hard drive has space. Because if you would only consume public data that lives in DataLad datasets, you would already be able to get more than 200 terabytes of data in this fashion, and you have access to this data without actually having to store it on your computer. And by using DataLad, you can also publish your own data in a way that others can retrieve it like this. Now, what is also cool is that I can also drop file contents to free up disk space if I don't need them anymore. I'm doing this with the DataLad drop command, and here I'm dropping the contents of one of those files that I've just retrieved. What this is useful for is that I can keep a very small sized link to the input data attached to the results of my analysis to, for example, enable recomputation, but don't use up much disk space with this provenance. So once I don't need data anymore, I can just get rid of it without losing access. However, you can't drop all data, and I will demonstrate this in the first dataset we've created. In this dataset, there are 2 comics, and I've downloaded one straight from the web using wget, and for the other one, I used DataLad download URL. The latter comic can be dropped safely. I'm showing you this right now. The reason for this is that DataLad registered the file's origin to it, and it knows from where to reobtain the file again. I cannot drop the other comic that easily, because there is no origin registered, and this results in a warning of potential data loss that I would need to override if I would be sure that I want to drop the file content here. Okay. The reason for this behavior and the fact that some data doesn't have file contents after cloning is due to the fact that most data in datasets is managed by the tool GitAnnex. I won't go into all of the details of these technicalities, there's a handbook chapter on that, but I'll briefly highlight the practical implications because it can be very useful to know about them. So data in datasets is either stored in Git or in GitAnnex. GitAnnex can, unlike Git, track files of any size, it can protect your files, and it provides means to transport your files so that data becomes as easily installable as software. But files that are stored in GitAnnex behave differently than files stored in Git. Their content is not present right after cloning and need to be retrieved. And even though I haven't showed you this, they are also write protected to prevent accidental modifications. So if you want to work with them, they need to be unlocked first. Now, by default, a DataLad safe would annex everything, because GitAnnex handles all file types and sizes very well. But it is useful to store small files that frequently change, such as code or README files in Git, because it makes it easier to work with them. And there are many ways to configure this, and one of those ways is, for example, procedures such as Yoda. What the Yoda procedure does is configuring the dataset so that anything in the code directory and the placeholder markdown files will be stored in Git instead of GitAnnex and are thus readily modifiable. So in this dataset that I've created, the README files versioned with Git and the comics, they are annexed, and thanks to this Yoda procedure, I don't need to care too much. It basically works out of the box for me. Now, the next feature that I want to highlight is that DataLad can link any number of datasets together. We call this nesting because with this feature, a dataset can include other datasets in a hierarchical order. A dataset that contains another dataset, just for terminology, is sometimes called a super dataset, and the included dataset is then called a subdataset. But apart from the hierarchy level, there's no difference between them. This feature of nesting has two advantages. First, it overcomes scaling issues. Some datasets that we work with, including ABCD, become incredibly large, and when they exceed a few 100,000 files, version control tools can struggle and break. By nesting datasets, and you will see a concrete example later, you can overcome this and split a dataset into manageable pieces. But importantly, you can apply DataLad commands recursively through datasets. So even though you have many separate individual datasets, if they are linked together in a hierarchy of datasets, this still feels like a single dataset. The second thing is that nesting allows you to link datasets as standalone, independently version-controlled units, and thus build up research from reusable and transparent modular components. This modularization is a foundation of the Yoda principles that I will get to shortly, but you can already in this graphic here see its immediate advantage. This nested hierarchy of datasets exposes the entire evolution of a research object, from raw data to process data to analysis results and published paper. And nesting makes each step and its predecessors not only transparent, but also potentially reusable, so that, for example, the process data can become an input to several analyses, not only to one. And when you share your paper or analysis with others, they can retrace every step that has been done in this hierarchy, at least those components that you share with them, and also build up on them. And likewise, with these modules, you can make sure that only, let's say, anonymized data is shared, so only modules that you actually want to be shared. You can, in this example, in this graphic, for example, keep the raw data completely private by just restricting the access to this dataset. Let me show you how to nest a dataset. I will do this in order to prepare my data analysis. And I'm doing it by installing a dataset that contains some input data on which I will later run a data analysis. The command that I'm using here is again datalet clone, but this time I'm using an additional flag, -d, which is short for --dataset, and that needs to point to the root of the my analysis dataset, which will become subsequently the super dataset in this hierarchy. If I execute this, it will download the input data from GitHub. And if I now take a closer look into the commit that this has created in my dataset, then you can see a couple of things that are registered inside of it. For one, you can see the URL where this dataset lived or came from and the path in the current dataset. And you can also see something that is called a subproject commit. If we now take a look into the history of the subdataset, so if I change directories inside of it and then query the git log, then you can see that the subdataset has preserved its standalone history, even though this is a really small history, and that its most recent commit identifier is actually the subproject commit that is registered as in the super dataset. So this links the subdataset in a precisely identified version state to the super dataset so that this data is registered in a precise version to the data analysis that I will be conducting. And that's great, because nesting now registers the origin and the location of a subdataset and also its version. Now, to quickly summarize everything about consuming data. The command to install a dataset is datalet clone, and you can use that on its own with just a URL and an optional path, or with the --dataset flag and a pointer to a super dataset root to install it as a subdataset. Datasets preserve their history, and you can get access to it if you clone it. If you install it as a subdataset, then the super dataset records only the version state of the subdataset, and the subdataset keeps its standalone history. After cloning, only files that are kept in Git and metadata about file availability of NX data are present. The file content of NX data can be retrieved on demand via datalet get, and if you don't need that file content anymore, it can be dropped with the datalet drop command. Now, before I continue with more DataLad basics, I want to briefly talk about a few concepts and rules for reproducible data analysis. Those rules are called Yoda principles, and if you apply them in your DataLad dataset, then you can create intuitively structured data analysis that are much easier to reproduce. The Yoda principles are guidelines on the structure, content, and handling of data analysis. They aren't limited to DataLad, but they can be really easily adopted if you are using DataLad. With regard to the structure of datasets, you should keep analysis components, so data, code, software, modular. As a rule of thumb, whenever something is a standalone entity and could be reused in another context, it should become its own dataset, and the individual components should then be linked to each other via nesting. A dataset for data analysis also needs to be portable and self-contained. This means it should include everything that is necessary for computations, and all components should be version controlled. It also means that scripts and other references should only refer to content within the dataset hierarchy and only with relative paths. This ensures that a dataset can not only be used on your own file system, but that you can move it to another computer and it will work just fine. It is also important to not obfuscate or muddy the structure. When computing results, you shouldn't save them to the input data, for example, but into the analysis superdataset, because outputs next to inputs reduce the reusability and clarity of the input dataset. And with regard to data analysis, you should define your computational environment as explicit provenance. You could, for example, create or use container images as portable software environments that allow yourself and others to redo your analysis on any computer. Luckily, DataLad can version control software images just fine, and I will show you this in a minute. And finally, during any step in a data analysis, you should collect and create and store as much provenance as you can, so that there's a digital trace of what has been done, how, why, when, and by whom. Now, let's take a concrete look into examples of applying the Yoda principles in a data analysis. You have seen that I have installed input data as a standalone dataset to keep my data analysis modular and reusable already. If I go up into my super dataset and then call the DataLad subdatasets command, then you can see that it is now listed as a subdataset. My super dataset has a code directory, and I will now add a script to the super dataset to perform a data analysis on the input data that I've just installed. Let me just print the contents of this script into the terminal so that I can echo all of this into a new script. And once this is printed, I will highlight a couple of concepts from the Yoda principles that I'm applying in the script. The script and the data here are a complete toy example. It's a k-means clustering analysis in Python on the well-known iris dataset that is used to classify different species of iris flowers by their sepal and petal width and length. And you don't need to pay much attention to the scripts or what it does, but here are a few parts where it follows the Yoda principles that I want to highlight. So one thing that I want to show you is that right at the start, it imports the DataLad Python API, and it then uses DataLad get to retrieve data which is referred to with a relative path. Further down, you can see that I am saving the results, for one, a plot, and then down here a prediction report with a relative path for one, and not into the input dataset, but into the super dataset. Okay, if I execute this command now, then I have a new file in my dataset. DataLad status reports this file is unchecked, so let me quickly save this addition to the dataset with DataLad save. And I'm also attaching a tag to just have another version identifier at this history version. Okay, now let me show you how you can execute the script in a way that captures plenty of provenance in accordance to the Yoda principles. And first I'm going to do this in the simplest way. The command I'm using for this is DataLad run. First of all, I'm making sure that I have a clean dataset state, because DataLad run will take any command line argument or any command line command. Let me quickly print that to the screen so that you can see it. In this case, the command that I'm giving to it is the execution of the script, and DataLad run will execute this command, save all of the resulting dataset modifications, and all of those modifications will then be associated with the command execution. That's why you need a clean dataset state before starting this command. What you can see that I'm also doing in this command invocation is that I'm attaching a human readable commit message. And this commit message will be under which everything will be saved. And there are two more optional arguments that I'm using here. For one, the -- input flag. I can use this flag any amount of times to specify paths to data or globs or complete directories or subdatasets that need to be retrieved via DataLad get prior to the computation. And the second one is -- output, and I use this flag to denote any files that would need to become unlocked for modification prior to redoing the computation. This sounds a bit cryptic, but it will become clear soon. So now when I execute this, DataLad will retrieve all inputs, unlock all outputs, at least try, execute the command and thus the script, and then save all of the results. And the result of this is not only the results of the data analysis, but also a machine-readable record in the dataset that includes everything I have specified as digital provenance and attaches it to the result. It's not really readable, but let me demonstrate what's particularly cool. Based on this record, you can instruct DataLad to rerun this analysis. To show you this, I'm cloning a published version of this dataset from GitHub. This dataset contains the exact same analysis, it's just that I've published it. And if I now take a look inside of this dataset, I can query one of the result files of how it came to be using git log. And then I can use the commit identifier that you can see here, and I can plug it into a command that is called DataLad rerun. And what DataLad does then, it reobtains the input data, it unlocks outputs for modification, and it will perform the exact same analysis again, which is absolutely fantastic. But it's still not optimal. So while this works really fine on my computer, it misses a very crucial part of digital provenance, and that is software. If I wouldn't have the correct Python environment for the script, then it can fail to run or reproduce. But there is a DataLad extension that can help. An extension for DataLad is a Python package that you can install on top of DataLad, and that adds functionality to DataLad. The extension that is relevant here is DataLad container, and you can install it via pip. This extension allows DataLad to work with software containers and thus includes software environments as digital provenance. I have already installed it, and here I'm going to demonstrate how I'm using it. So first of all, I'm going back into my own analysis dataset, and now I'm using the DataLad containers add command to register a software container into my dataset. I can register any amount of container images. Here you can see that I am registering a image from a Singularity Hub URL, and I'm saving it under the name software in my dataset. Once I have attached a software container, you can see that it's currently downloading it. I can not only share this software container together with my dataset to include software as provenance and as a part of my data analysis, but I can also include information on the software container into a run command. And I'm doing this with the DataLad containers run command, which works pretty similar to DataLad run. It's just that I'm also attaching information on which container image to use. In this case, I'm identifying it with the name software that I have given it. Okay, so when I execute this command now, the command is executed just as before, but inside of the container. and the container is included as additional provenance into my run record. And because everything is now version controlled and tracked, I can precisely identify any difference that occur between reruns. Now, if a run or a rerun does not lead to any modification in the dataset, there will be no entry in the history because there's nothing to save. So, for example, you can check if your analysis yields identical results on two different computers just by rerunning them and seeing if something is saved and thus changed. You could also do this after code refactoring to see if everything still works as expected. But if a change introduces a difference between previous output and recomputed output, then only those files with differences are saved, and then you can use Git tools to investigate the precise difference. So, as an example, let me update the color scheme of the figure from muted to blues. I'm doing this from the command line again with the stream editor set. If I take a look at this change, you can see I'm just changing the color palette, and now I can save this change. And if I now rerun the last run commit, I'm identifying it here with the Git terminology head1, so the second most recent commit. Then this rerun shouldn't result in a change of the prediction report, but it should result in a change of the color. And I can verify this by taking a look at the history. For example, I could use a git diff between the current state and the state before that, and you will see that the only modified file is the pairwise relation PNG file. And I can then investigate the precise differences between those files because both of them exist in my history. I can check them out and then pick whichever version I need. So to quickly summarize the reproducible computation features, the DataLad run command can record a command and its impact on a dataset. Whatever the command produces will be saved, so you should use it in a clean dataset. Everything that you specify as input will be retrieved prior to the command execution, and everything that's specified as output will be unlocked for modification if the command is rerun. If you want to capture computational environments as provenance, you can use the DataLad containers extension to add software images to your dataset and run commands inside of them. And if you want to then redo a computation that has been performed with containers run or run, then you can use DataLad rerun to automatically re-execute commands later based on the provenance that you have collected. Now, before the session ends, I have one last thing to highlight. You've seen that DataLad makes data retrieval fantastically easy. And let me assure you that you can get plenty of data as DataLad datasets. For example, all OpenNeuro data or the Human Connectome project dataset. At the time that I'm recording this lecture, retrieving ABCD data is not yet possible with DataLad. What is difficult for us is that the ABCD dataset contains file names with GUIDs, and those file names cannot be shared publicly, which makes it difficult. The good news, however, is that it is in principle possible, and there's a chance that by the time you're viewing this lecture, there is an ABCD DataLad dataset available that you can clone if you authenticate with NDA credentials that have appropriate access. My colleague Jarek, whom you will meet next week, has already transformed the ABCD data into a large nested DataLad dataset, and I will use the last few minutes of my lecture to show you the looks and feels of this dataset just so that you have an idea. Let me clone this dataset, and for this I'm going outside of my analysis dataset. First of all, I'm cloning the dataset. Note that I'm cloning it from a private web server here. This web server is a web server where only few people have access to. If there is an ABCD DataLad dataset by the time you see this lecture, you will get a URL that you can replace the URL that you're seeing here with. Let me download this data, or let me install this dataset now. You can see again that it is really fast, but this dataset is obviously super large, and because it's so large, it is split into a hierarchy of nested datasets. here's a schematic overview of how this looks like. So there's one super dataset, the one that I've just cloned, and this super dataset contains one subdataset per participant. And each participant can also contain additional subdatasets. And this splits the vast amount of files in the ABCD data between thousands of datasets. Now, here is how this dataset looks and feels like. After cloning, the dataset contains about 10,000 subject directories, but it is super small in size. Each of the directories that you can see here is a subdataset. So if I execute datalet subdatasets, then that command will get really busy. Each of these directories looks like a directory, but because it's a subdataset that has only come with the super dataset but hasn't been installed yet, these directories appear to be empty. In order to browse the files how you've been used to and how you've seen it in the study forest dataset, you need to install it, and the datalet get command can do this for you. If you want to only install a dataset but not download any data, then you can attach the --no data or short -n flag, and that will only install the dataset so that you can browse the files and then retrieve data on demand. If you would want to install all of the subdatasets, you can run datalet get with a --recursive flag from the top level dataset, but note that this would take a while, but it's possible and enabled by those recursive operations that I've mentioned. One thing that you need to be aware of is that you need to do a small detour if you want to retrieve data from subdatasets that aren't yet installed. Let me quickly show you how to retrieve data from an installed subdataset. Here I'm just retrieving the data from this one subject. And that works just fine. But back at the start of the session in the study forest dataset, I had used an asterisk character to let my shell expand this character to match patterns, and that allowed me to get a bunch of files at once. If I would try this like this in order to get several subjects data, so I'm expanding over subject identifiers here, then this will not work if the subdatasets are not installed. Because in this case, where there are no file paths available due to the subdatasets being not installed, the shell can't expand to any of that. So what I need to do is I either need to install all of these subdatasets first, or I can get creative and I can explore the capabilities of your shell. So you've already heard how powerful a tool your shell is, and here is an example on how I can flexibly use the capabilities of my shell to overcome the limitation with expansion. So the first thing that I'm doing here is a bash for loop, and this bash for loop loops over all subject directories, and then based on the directory names it constructs paths to the files that I want to retrieve for all of the subjects. And I'm writing this into a simple text file via redirection. And what I can then do is I can pipe the contents of this file into a datalet get call. And for this I'm using the Unix xargs command, which allows me to pass what is happening on the left of the pipe, all of the file names, as an argument into what comes after the xargs command, datalet get. And xargs even lets me parallelize this with the -n argument so that retrieval of many files is sped up, and here I'm parallelizing 20-fold. That means I'm running 20 parallel get calls at once. There are more tips and gists like this in the Datalet handbook, and if you follow the URL up there, you can read all about them. So, as we are at the end of the session, here's a quick summary. Datalet has a lot of features. If you use Datalet, then you can version control any file easily. You can create, share, and use digital provenance of your data analysis, and you can even have a machine redo previous analysis and verify the reproducibility of your results. You can consume large amounts of data easily, maybe, hopefully even the ABCD dataset, and you can make sure to be transparent and clear in your work. But even though this session has been intense, there's a lot that I haven't talked about or demonstrated. Luckily, it is all written up, and if you want to learn more about DataLad, then you can. There is extensive user documentation in the DataLad handbook. There are recordings of tutorials and workshops on our YouTube channel, and there is a matrix channel where you can interact with other users and the DataLad developers. And with that, I want to thank you for your attention. I'm looking forward to the QA session, and I'm looking forward to seeing you virtually. Take care, stay healthy, and bye-bye.